Hi, all, and welcome to part three. I left you and we were talking about valence, right, which is the outermost shell. Okay, so valence electrons are those that are found in this outermost shell, valence shell. And so I have blown up this portion of this version of the periodic table. So you can see here hydrogen, lithium, and sodium. And the reason that I blew it up is because I wanted to show you that each one of these elements has only one electron in its valence shell, right? Hydrogen has its only has one electron, and so that electron sits in its first shell, which is its valence shell. Lithium has three electrons. How do I know? Well, three protons, and then since it's electrically neutral, it has three electrons. The first two electrons go into the first shell, then that shell is filled with two. So its third electron goes into the second shell, like you see here. So it has one electron in its valence shell as well. Let me circle that so we can see that, right? So that's here. Sodium has 11 electrons because it has 11 protons. Two go in the first shell, eight go in the second shell because that second shell is filled up with eight. And then its 11th would go into the third shell. Circle it here. Maybe a little bit hard to see. Okay, so these three elements, right, even though they have very different numbers of protons, behave similarly in a chemically speaking because they only have one electron in their outermost shell, whatever it is. Whether it's the third, the second, or their first, their valence shell has only one electron. And the chemical behavior of an atom, right, is mostly determined by its valence electrons. So not the electrons in its innermost shell, or innermost, or in this case, this would be innermost. This is an inner, right? This is its only shell. So it's not the electrons that fill the inner shells, if there are inner shells. It's the ones, it's the number that it is in the outermost shell, the valence shell. Okay, but at this point, I want to show you something else. What about if the outermost shell is filled? So if you're looking at helium, for instance, it has a filled outermost shell. It only has one shell, but that shell fills with two, and it has two electrons. It has two electrons there. Neon has a filled outermost shell. It's the second shell, and it's filled with 8 electrons. Right, I put that there. Right, neon has the first two. It has 10 electrons total. How do I know? 10 protons there. That means 10 electrons total. Two go into the first shell, and then the first shell fills, and then the remaining 8 go into the second shell, and now that shell is filled. So elements with a full valence shell are chemically inert. They don't like to participate in chemical reactions. So we call these the noble the noble gases. This is as bad as when I draw with my mouse. Okay, the noble gases. That's what we see here. Okay, so helium, neon, argon, they're all chemically inert and they have outermost shells. It makes them very stable. So they have no tendency to want to take another electron on, give off an electron, or share an electron. They don't need to. They're nice and stable based on the filled valence shell that they all possess. Okay, so these atoms, they're grouped, right? They're grouped going down based on the number of electrons in their outermost shell, right? So it's not based on, in this case, how many protons, right? Beryllium has 4 protons, quite different from magnesium's 12 protons, but they behave similarly because they both have 2 in their outermost shell. How can I tell? Well, I can count, right? 12, I know that means 12 protons, 12 electrons. 2 go in the first, right? So then there's 10 left. That means 8 go into the second, and then there is 1 and 2 in the valence shell of magnesium, which happens to be the third shell. And there's 2 in beryllium. That's much easier to see, right? Beryllium has 4 protons, therefore 4 electrons. The first 2 go in the first shell, then it's filled, and then the second 2 go into the second shell, which is its valence shell. They have 1, 2 right there. Therefore, beryllium and magnesium have the same number of electrons in their valence shell. They behave similarly in terms of whether or not they want to bond or give off electrons, as I'll be showing you. Pick up electrons, I will show you. Okay, now we have to go back to the idea, and I mentioned this before, of what an electron orbital is, because these shells are really nice, but we have to get a little bit more specific about where these electrons might be buzzing around the nucleus. So I defined it before, and I had it on an earlier slide, and I bring it back again. An orbital is the three-dimensional space where an electron is found 90% of the time. So it's a three-dimensional space, right? This does not tell you if we look at these concentric circles like this doesn't tell you the space that an electron may be found in. It's basically like the average distance from the atomic nucleus where an electron might be found, but it is not telling you anything about where these electrons might be whizzing around, as my cursor was trying to show you there. The orbital is the space where you might find the electron whizzing through. Okay, so each electron shell that we have met now contains electrons at a particular energy level. We know this. All the electrons in the second energy level have the same energy, same amount of energy. But these, where the electrons are distributed, can be different, right? And they're going to be distributed among a specific number of orbitals, and these orbitals each have distinctive shapes and orientations. So within a particular shell, you can have multiple orbitals, and those orbitals can have different shapes from one another and can be in different positions. Let's take a look. So we're going and trying with neon again, right? Because it becomes interesting when you have multiple electrons, because that's when you start to see the multiple shells with the orbitals within the shells. So here's your first shell, right? Within the first shell, the orbital is known as a 1s orbital, and the electrons would be found and the spin whizzing around basically in this type of space, right? Which is a bit of a sphere. Okay, so the next electron, the second shell, has actually multiple orbitals, right? The 2s orbital, it's called, because we're in the second shell. Oh, right. 1 comes from the first shell, so it's the 1s orbital. The second shell, you'll notice that there's a 2 in front of everything. So it has 1 2s orbital and 3 2p orbitals, right? And the orbitals are at different angles. So the p orbitals are dumbbell shaped. Let's see if I can, they've outlined them in different colors. It actually helps here. So let me just use the red to outline the red one. So here would be 1 p orbital, right? And then if I follow their colors, here is, and they said, so the p orbitals are said to be dumbbell shaped. I really made a mess of that. Yeah, that's another p orbital. And then the third p orbital is in the blue, is outlined in blue. So it's said to be along, they're at right angles to one another. So you have one at the x-axis, one at the y-axis, and one at the z-axis. So the second shell we know fills with 8 electrons. There can be only 2 electrons in each orbital. So 2 go into the 2s orbital, right? And 2 electrons in each of these other, right, 3. So maybe that's the simplest way to do it, is go like 2, 2, 2, right? Because remember though, it's a dumbbell shape. So 2 can be whizzing in this dumbbell shape, 2 can be whizzing in this area. It's defined by that shape, and 2 can be whizzing along in that area. So that's how you get up to the total number of 8. No more than 2 electrons in each orbital, and the second shell has 4 orbitals. One is called the 2s orbital, and the other 3 orbitals are known as p orbitals, right? And they're looking like that. They're positioned like that at right angles to one another. So if you superimpose all of the electron orbitals on top of each other like this is what it would look like for neon, right? It would look like the electrons are found, so it's showing you the 1s is in the middle, then the 2s is sort of right in that space, and then here are your p orbitals. So this is telling you, it's telling you how well, no, sort of where electrons will be whizzing around, right? Because they're not orbiting like a planet around the nucleus, right? Because the nucleus would be in the center here. They are spending time going around. Yes, they are attracted to the positive charge in the nucleus, but they're not moving in a predictable pattern. So the orbitals help you to know where they might be found. And if you took a snapshot, an electron might be here, and then nanosecond later it's over here, and then it might be back here, and then it's over there, and then it might be here and up there, right? But the idea is that the orbitals, that particular electron will stay 90% of the time in this particular space that's defined by this figure 8, which will be the only one that I circle in this because I want you to continue listening. And I know my drawings might make you want to turn it off. Okay, so that's the idea. These are not individual electrons. This is the same electron. This looks like a smiley face now. These are individual. This is not individual electrons. It's the same electron, and I was trying to show it to you moving through space. I have a little video that might help. Okay, so far, if you look at what we've spoken about, this is like a bit of a summation slide, so I kind of like it. We know that we have an atom. An atom is made up of subatomic particles. It has protons, positively charged, right, subatomic particle that's found in the nucleus, as well as neutrons, these particles also found in the nucleus. So the protons and the neutrons are found together in the atomic nucleus, and they make up the atomic nucleus. Okay, and then whizzing around, not concentrically moving like this, even though this is very neat. They have to have a neat way of showing it to you, but whizzing around all over, well, I mean, there's just two, so actually it would be whizzing around a spherical spaces if this was 1s. Right, are negatively charged electrons, forming a negative cloud, right? So these electrons would determine chemical behavior. If we're back to looking at helium, right, with its 2 protons and its 2 electrons, its outermost shell, its valence shell is filled. So it's nice and stable. So in terms of chemical behavior, it's going to snub its nose at other atoms. It's perfectly fine as it is. It's nice and stable. So this particular one has a filled valence shell, doesn't care. Okay, let me find my little video, which might help. Okay, I found this little video and I watched the beginning, and I figured sometimes it's nice to just put it right where we're learning about. So that's why I started it here, but feel free to look up this video called How Small is an Atom, Jared Owen, if you want to know what happens at the beginning. Okay, here we go.
This is made up of protons and neutrons. These electrons were tricky. At first we thought, they have to be doing something, so they probably revolve around the nucleus like this. Electrons were then discovered to have different energy levels. We call these shells. Shells can only fit a certain amount of electrons. The more electrons, the more shells. It didn't take long before we realized that these shells don't determine how close the electron is to the nucleus. As it turns out, electrons are a lot more unpredictable. So if electrons don't orbit the nucleus, what do they do? Let's start with an idea of an orbit. Here we have the Earth going around the Sun. If the Earth is here today, we can use the laws of physics and gravity to predict exactly where the Earth will be 3 months from now. We know both where the Earth is and where it's going. Now let's go to the size of an atom. With an electron, things are a little different. We can't know exactly where it is and where it's going. We can only know one or the other at any given time. This means it is impossible to really know what the electron is doing. The best we can do is predict where the electron will be found. This area is most commonly known as the electron cloud. However, if we want to be more specific about where to find electrons, you'll need to know about orbitals. This is not the same as orbit. Orbitals are specific shapes where electrons live in. If you were in a college chemistry class, you'd be studying about how these orbitals fill up as you get more electrons. But I'd like to keep things simple for this video. So in short, electrons are uncertain. We can't know the path that they travel, only that they'll be found here in the electron cloud. So now you know that even though this is a popular way to represent an atom, it can be misleading. Just to recap what we learned, everything is made of atoms. Atoms are incredibly small. The nucleus is even smaller, and electrons don't orbit the nucleus. Their path is unpredictable. Thanks for watching, everyone. My name is Jared Owen, and I'll see you next time.
All right, so let's get back to the idea of valence shells and what that means about chemical and behavior. So if an atom has an incomplete valence shell, outermost shell, it has a couple of options to fill it. Because if we remember, if we go back to this slide, we can see here that something like helium or neon or argon, those that have completed outermost shells, they don't want to participate in any kind of chemical bonding with others because they are stable and there's no tendency to move from stability to instability. Now, these other ones, though, if I move this a little bit out of the way, the other atoms, let's say in this particular row, is that they all have, until you get to argon, they do not have a complete valence shell. So they will have a tendency to want to behave in a particular way, right, to fill their outermost shell. Now, it may be easier if you're something like sodium or magnesium to give off these electrons to fill your outermost shell, because then what you would do is you would get rid of the third shell if you're sodium and you drop down to having a full second shell. So that's something that atoms can do as well. They don't have to gain electrons to fill their outermost shell. Sometimes they drop it and then they have a full shell, the shell right below. Something like chlorine, though, it's only missing one electron in its outermost shell. So it has a very, very strong desire to pick up an extra electron, and then it fills its outermost shell that way. So let's take a look. So it says atoms with incomplete valence shells, so they're not as stable as they could be, can share or transfer. I was just talking about the transfer, right, with sodium and chlorine. They can transfer electrons that are in their outermost valence shell with other atoms, and it's all in a desire basically to complete its outermost shell. They can do it in two ways. They can give off, right, transfer them, right, accept, right, or they can share electrons. And when they share electrons, then they're held together by what we call chemical bonds. Because when two atoms share an electron, the atoms get close to one another, right? So that the electrons of one are attracted to the nucleus of itself, and I'll show you also to the nucleus of the atom it's participating in a chemical bond with, right? So the sharing of electrons is going to be called covalent bonds. It results in the formation of molecules, right? So molecules come about because atoms share electrons and they get a chemical bond through that share. So let's take a look at what it looks like. So this was the word that I mentioned. I'm sure you know it's called a covalent bond. So that results when atoms share a pair of electrons that are valence in their outermost shell. So let's take a look. We know hydrogen only has one electron, right? It has one proton, is signified by this positively charged little fuchsia ball. That's what you see there. And then it has one electron whizzing around it, I told you, in the first shell, and that orbital is called the 1s, right? The orbital of the first shell is called 1s. So the electron of each one of these hydrogens is whizzing around in this area. It can be found anywhere within this area 90% of the time. And this is the same. Anywhere within the area, this area that is highlighted in yellow, right? 90% of the time. In a covalent bond, it says the shared electrons count as a part of each other's valence shell. So this, when atoms get close enough, right, each electron is attracted to the other atom's nucleus. And that's why if I draw here, you can see it has more of this shape. And now in this picture, we sort of see that the electron cloud looks more like that, right? Because the electron can find itself not only attracted, it says here, its own nucleus still attracts it. That's why you still find it whizzing around here as well. But it can start to now whiz around here farther from this nucleus and closer to the nucleus of the atom that it is going to be attracted to and participating with, right? And then ultimately, right? When, excuse me, the two atoms are close enough together, then you find the electrons whizzing around both. So this hydrogen molecule now, these are two atoms that are sharing electrons, and they're sharing electrons held together by what we refer to as a covalent bond. So if there was one electron here, I'll put it as a dot, it could only be anywhere here, switching around, whatever. Now this same electron can be found here, but can also be found at any time somewhere here, right? And if I make the electron of the other hydrogen atom in green, right, originally it could be found anywhere here. 90% of the time it's going to be found in this type of orbital, right? And then now all of a sudden, ooh, that was so loud, sorry. Now all of a sudden, right, it can be found here, and now, right, it can be found like that. So this is important. In a covalent bond, the shared electrons, so each one of these atoms now has the benefit of the other one's electrons. That's why they're shared. So the electrons count as a part of each atom's valence electron. So because both a green and a red electron are whizzing around hydrogen atom number 1, this is hydrogen atom number 2 in my little example, because both a red and a green electron are whizzing around hydrogen atom 1 and hydrogen atom 2, it's as if both has 2 electrons circling it in an electron cloud. So this means that they have both. Each hydrogen atom has finished its valence shell. It has filled its valence shell because it's as if they went from having just 1 electron whizzing around it to 2 electrons whizzing around it. So that's the strength. That's what holds these two nuclei together, is the electron cloud, right? The electrons that are whizzing around both of them, attracted both to the original atomic nucleus that they were associated with and to the second atomic nucleus, because they got close, the atoms got close enough together, right? So now the electrons are circling around both of these, right? And can be found in either of these orbitals. So this is a strong bond as we know it. It's a bond known as a covalent bond, and it holds two atoms together, right? And it's the sharing of electrons. And when I come back for the next segment, I will be showing you all the different ways in which we can depict a covalent bond when we're looking at it. All right, so it's the sharing of valence electrons, a covalent bond, for purposes of completing the valence or outermost shell of each individual participating atom. Okay, see you next time.